Welcome back in the plenary, and I hope you've enjoyed the posters and the break. And slowly go on with our program. I first would like to remind you that you've got the power to vote for the audience awards. And to get more details on how that works, please check the website where there's awards section, and you will find all the information regarding how to cast your vote for the audience awards. I've also been asked to again remind you of the gala event tonight. We will get more information here later today, but be prepared, get your drinks and whatever you need to create your cocktail for tonight. But before we get into cocktails, it's time to get even deeper into machine learning. I'm quite excited to hear Bernhard Schirkopf's talk. But to get there, I'm handing over to Floris and Jan, who will take us into machine learning now. Jan.
Thank you, Alex. It's my absolute pleasure to introduce today's keynote speaker, Bernhard Schirkopf. Bernhard is a director of the Max Planck Institute for Intelligent Systems in Tübingen and holds a professorship at ETH Zurich. He's really known to everyone for his groundbreaking work in the area of machine learning in all disciplines, in particular on support vector machines and on kernel methods. And his work has been cited over 170,000 times, and he's in the list of top 15 distinguished scientists in all of computer science. There actually aren't many prizes, many major prizes that Bernhard hasn't been awarded. The prizes include the J.K. Agarwal Prize for the International Association for Pattern Recognition, Academy Prize of the Berlin-Brandenburg Academy of Sciences and Humanities, the Royal Society Milner Award, the Leibniz Award, the Kerber European Science Prize, and the BBVA Foundation Frontiers of Knowledge Award. He's also a member of the German Academy of Sciences and an ACM Fellow and an Amazon Distinguished Scholar. And in addition to being a board member of NIPS and IMLS and co-editor-in-chief of JMLR, he's also co-founded the Machine Learning Summer Schools. And today he's going to talk about his current work in the area of causal learning. I would like to remind everyone that you can feel free to pose any questions in the chat at any time. And Bernhard, we're honored to have you here, and the stage is yours.
And thank you very much, Floris, and thank you to the other organizers and to the audience. So let me start by saying what all speakers say at the beginning. Let me start by sharing my slides. So hopefully you can now see my slides. So I would like to speak about causality in causal learning, and specifically with the focus on high-dimensional observations, which I think is maybe the area of causal learning that's particularly relevant to medical image processing. And let me start by like a personal note, how what I was thinking about when I got into this field, and what kind of problems kept us busy. So I originally started doing work on neural networks in 1993 as a student and as a master's student. And I then moved to statistical learning theory from there. And about maybe 10 years or so later, I got interested in causality. And so first we were just using machine learning to build better causality methods, for instance. So we came up with kernel-based independence tests and kernel-based conditional independence tests, which are used in causality, etc. But then at some point we noticed that it also goes the other way around, that we can actually use causality to better understand certain machine learning problems. And a standard problem that we discussed a lot in those days was this neural net tank urban legend. So in this urban legend, there's a neural network that's trained by the army in America to distinguish, or by some contractor, I don't know, to distinguish Russian tanks and American tanks. So there are different versions of the story. So it's just the gist. And they find that they can do 100% correct. So everybody's enthusiastic, but maybe someone is a little bit skeptical and says, well, let me try if it also works on this other set. And then they had another test set, and the system performed at chance level. And they started to dig in and noticed at some point that the original neural network that was 100% correct had just focused on some spurious feature. Let's say the color of the sky. Maybe all Russian tanks were photographed on a cloudy day and all the American tanks on a sunny day and the sky is blue. So this was, of course, a problem, because such a system is then has, if it focuses on such a feature which is just correlated or spuriously associated with the target, then this kind of classifier won't be robust at all with respect to changing circumstances. And I was hoping at that time that if we can build systems that take into account causality as opposed to just correlations or statistical dependencies, we could make them invariant with respect to this kind of changes. Now, this is a funny story, and you probably all heard this story before, and it's particularly funny because the army is screwed up, and we can all laugh about that they did something really stupid. But the question is whether we are much smarter now in the community. Of course, we have much more accurate systems. For instance, we have better object recognition systems. But one could argue that essentially the problem is still there. So in this case, for instance, if a cow, which maybe in the training set is mostly on a green meadow, appears on a beach, then suddenly it's not recognized as a cow anymore. So if there are things in a test image here, beach or the sea, that are negatively correlated with the presence of the cow, then recognition fails. And of course, this is because machine learning looks for correlations. That's how it's built. And it doesn't care about causality fundamentally. So we shouldn't blame the algorithm. It does exactly what it's trained for. And the same holds true in the case of adversarial vulnerability. So if the system is very much optimized on a given distribution, then it's not necessarily robust with respect to even very small interventions. And so if we add a little bit of malicious noise to a test image, then even if it's imperceptible to a human, the system may suddenly classify this piglet as an airliner. So this is a problem. I think we're getting increasingly aware of it. And once we leave this comfort zone of IID data, so data which is independent and identically distributed, so it comes from one random experiment, one distribution, and the future data comes exactly from the same thing. So once we leave this area, once we start talking about interventions and shifts, we actually have to start thinking about causal models that underlie statistical models. And I found that, and that's also the purpose of the talk, that maybe many of the open problems in machine learning actually are related to this. So we have to go one level deeper to the causal models that give rise to statistical dependencies in the first place. And so I want to tell you a little bit about that and also show you some applications that use this kind of links. And I want to start with maybe the first person who understood a fundamental connection between statistics and causality, and that was the philosopher Hans Reichenbach, who postulated in the so-called common cause principle named after him now, that if we find two observables to be dependent, then there exists another observable which causally influences both of them. And so this generates the dependence between x and y. And this third variable can be chosen such that it screens x and y from each other, which means that conditioned on z, x and y become independent. So it explains all the dependence there is. So that means in the generic case, we have a setting like this, which could degenerate to one of those two settings here. So z could coincide with x or y, but it doesn't have to. So the standard example is the frequency of storks and the human birth rate are correlated with each other in European countries, at least at some point they were, which means there must be a causal explanation, which could be that the storks bring the babies, could be that the babies attract the storks, or there's something else that causally influences both of them. For instance, I don't know, environmental pollution or industrialization or whatever. Now, these three settings cannot be distinguished based on just observational data of x and y. So we need additional principles. But before we get into that, I want to say that this basically the Reichenbach principle and this idea of conditioning and how conditioning is related to graph structures is generalized in causal graphical models or structural causal models. And the structural causal model consists of a set of observables that lie on a DAG. The arrows in this DAG directed a cyclic graph. They represent direct causation. And each variable is a function of its parents, a deterministic function of its parents, and a noise variable. So there's a noise variable at each variable, and the noises are jointly independent. If they were not, we would go back to the Reichenbach principle and say there's a dependence that we need to explain by a more complex graph structure. But so let's assume they are independent. And now you can imagine that you put these independent noises here in one at each node of this graph, and you let them spread according to the graph topology. And then the distribution, as these noises spread around, you will end up with a distribution over the x variables, which contains information about the graph topology. Because these independent noises initially in the use, they start mixing with each other according to this topology. And the way you find out about this and the way you recover aspects of the graph structure is by using what's called the causal Markov condition, which states that conditioned on its parents, each variable is independent of its non-descendants. And this means we can test for causal structures, provided we can run conditional independence testing, which is actually a hard thing to do in high dimensional and continuous cases. But suppose we can do that, we can find out about causality, provided we have at least 3 variables, because a conditional independence test always connects at least 3 quantities to each other. What we get at the end is also called a graphical model. And we get a particularly nice factorization of the joint distribution, which corresponds to this graph. And in this factorization, it's the joint distribution, which is entailed by this graph and the independent noises, is written as the product of conditionals, one conditional for each node. And the conditionals only condition on the parents of the node. So this is a factorization that respects the causal structure of this generative process, which is written in terms of these equations or assignments, which are called structural equations or structural assignments. So that's a particularly nice factorization, and we'll come back to that later. And just before I move on, what's the beauty of this kind of model, which entails a probabilistic model? But the beauty of this one is that here we can make interventions. So we can, for instance, we can set a variable to a constant and then see what joint distribution does that entail, or we can shift the variable by some number or change the mechanism at one variable, etc. So this is a richer class of mechanisms. Okay, so I'm going to skip this and instead go to this thing. So I mentioned before that if you have only 2 variables, there's nothing you can do in terms of conditional independence testing. So we thought a lot about the problem with 2 variables, and we came up with an assumption which sometimes also helps us in the case of just 2 variables, and which one can also use if one has more variables. So it's kind of additional information that you can use for inference. And the way I like to introduce it is using this object, which is a so-called Béchet share. So it's a famous visual illusion, which was done by an artist. So in general, so you can see it's 2 pieces that are separate from each other, and whenever we look at an object, I would claim our brain makes the assumption that the object out there and the process that sort of transforms the object into a perception, so let's call it the mechanism, are independent from each other. And we can highlight this assumption by violating it. And in this case here, so first of all, we write it a little bit more generally. We say, let's assume the causal generative process is composed of autonomous modules that do not inform or influence each other. Now we can violate it in this case by coupling the perception, in particular the perception direction, and the object to each other by looking through this little hole here. And if we do that, perception fails because we see an object which isn't there. So and most visual illusions build on violating implicit assumptions of the brain. So we think that this is a good implicit assumption, a good inference principle, if you want. And to explain it slightly more mathematically, but still intuitively, let's assume we have 2 variables, both just on the interval 0, 1. And so x and y, and let's assume x is the cause, y is the effect, and let's assume we have a function. So that's now our mechanism. Note that this is even a deterministic function, so there's no noise. So this is like if you like a degenerate case of a conditional or a degenerate mechanism, if you want, that relates x to y. So we first pick some distribution over y, then we plug it through this mechanism. This leads to a distribution over x. And question is now, given only the data that we observe and not knowing what was the cause, what was the effect, can we infer what was cause, what was effect? And the claim now is if we assume that we choose the input so that we choose the cause and the mechanism independently, and the claim is we can, because if we choose these things independently, then this thing doesn't know about the shape of the function and where the function is flat or steep. However, the output distribution then does know, because wherever the function was flat, the output density will have high mass or large values. And this can be formalized, this principle, by looking at a certain covariance between the input or between the density and the log of the derivative of the mechanism. And we can prove that if this covariance vanishes in the causal direction, so this is now the assumption of independence, then the same covariance in the anti-causal direction will be strictly positive. So this is something that in principle we can test based on data, and one can also justify it in terms of information geometry and other ways, but I won't go into details on that. And maybe I will also keep this one very short. This is just to mention, so this whole thing, so I've talked about, I started with statistical structures, and then I said, well, sometimes it's better to go one level deeper and talk about causal structures. But these causal structures still had some statistics built in, because the noise variables were statistical random variables, independent random variables. But we can also start with something different, and because the causal structure is the fundamental one, where in a sense the interesting causal structure is the mechanisms and not the noises. And if we instead use, so if we take as mechanisms programs running on Turing machine, so these U's are the programs. They take as input the values generated by other nodes and produce an output. They all run on a joint Turing machine, on the same Turing machine. So if we do it this way, and if we assume that the programs, which are now what that noises were before, are jointly independent, in the sense that a joint compression of these programs, each of which is a bit string, does not save space compared to individual compressions. If we assume this, then we basically get a complete theory of graphical models that don't use standard statistical information, but use Kolmogorov complexity and associated independence measures. So one could also, depending on what assumptions one puts in, one gets causal structure in different domains. And I won't go into detail on this. I just want to mention that, interestingly, with this formalization, one can actually derive the thermodynamic error of time from first principles, in this case, from the independence assumption. So so it would be possible if you have a physical scattering process where you have some particles flying in. So this is the cause. And then you have a non-trivial object that scatters. That's our mechanism. And you have an outgoing beam, which now carries information about the object. That's how photography works. The photons carry information about the objects they've been reflected from. And then it turns out, if we assume that this incoming physical state is independent from the mechanism, or in this case, the physical time evolution, then, so this is now our independence principle. In this case, measured by Kolmogorov complexity. If we assume this, then we can prove that the Kolmogorov complexity of the state is actually non-decreasing under the time evolution, so which means the entropy cannot decrease. And so this is just because I like that. I like this other kind of application. I just wanted to briefly mention it, and hopefully you haven't spent too much time on it. So I want to come back to machine learning proper by pointing out that it turns out that this independence assumption has also some non-trivial implications for machine learning. In particular, when we relate the direction of prediction and the direction of causation to each other. So sometimes we solve machine learning problems where the prediction is aligned with the direction of causation, and sometimes we solve problems where this is the opposite. And I've given some examples here, but maybe it's not important to go into details on that. But what's interesting is now if we make this assumption that the distribution of the cause and the mechanism are independent, for instance, in the sense that I showed you before when we had this one-dimensional function. So suppose this is our assumption, and suppose we want to learn a mapping from x to y. So we want to estimate properties of p of y given x. For instance, if we want to do regression estimation, we want to learn the expectation of y given x. Now, suppose we want to do this, and now we look first at the problem of semi-supervised learning. So what does semi-supervised learning do? It tries to improve our estimate of p of y given x by having additional data of p of x, so unlabeled data. Now, if x is now coinciding with the cause, then actually our assumption says that those two things know nothing about each other. So having additional data of p of x shouldn't tell us anything about p of y given x. So in this case, semi-supervised learning should not be possible. In the opposite direction, however, it should be possible because, as you've seen in the toy example before, in the opposite direction, the two things should have something to do with each other. And it turns out for the problem of covariant shift adaptation, it's basically the other way around. So depending on which direction you're learning, the underlying causal structure has implications for machine learning problems. So even though we've always dealt with statistical problems, we have sort of intuitively already come up with methods that exploit certain underlying causal structures. And we've come up with assumptions to explain why our methods work that can be, or that I think are best interpreted in terms of causal assumptions. So these assumptions here that are often referred to in semi-supervised learning are actually assumptions about links between these two objects. And I will skip this thing. So we've also recently applied it in natural language processing. So first of all, I should say this works in the sense that if we look at existing benchmark studies in semi-supervised learning and categorize problems into causal and anti-causal, it beautifully aligns with these predictions. But also more recently, we found that actually it also quite well aligns with in a number of different NLP tasks. So we've categorized certain NLP tasks here, and it turns out most of the time we get nice agreement with what we were expecting. We've also applied something related recently to a problem of exoplanet detection, which I think I'm going to skip over. I'll just mention that we found using this, we found about 20 new exoplanets, and it turned out one or two years later, one of them got famous because, and this is just a strike of luck, but one of them turned out to be later the first exoplanet that was lying in the habitable zone, so in the zone around its host star, which allows liquid water. And people found, so the first one in the habitable zone where people actually found traces of water in the atmosphere using spectroscopy. So I want to switch gears a little bit and use the last 15 minutes or so, or I don't know, according to my watch, I should have that. Please stop me otherwise, on something which sort of brings together causality and machine learning in a high-dimensional setting. And to do this, I want to first rewind a little bit in time, go to Herb Simon. It's 1956. He was predicting that machines will be capable within 20 years of doing any work humans can do. And this prediction was fueled by this surprising progress that, so this was the founder of, I don't know, classical AI, maybe of all of computer science, one of the fathers of computer science. There was impressive progress on problems that people considered hard, like computer chess, etc. But problems that appeared simple, such as most things animals could do, turned out to be very hard. And this came to be known as Moravec's paradox. Now, in hindsight, we're always smarter. Of course, nowadays we would say it was naive of classical AI to assume that we can realize intelligence simply using programs written by humans. After all the existing examples of intelligent systems, humans, animals, they appear much too complex for something that a human could program. But there's a second problem that's maybe less often talked about, which maybe is even the bigger problem, which is for symbolic AI, which is where do the symbols come from that we should write programs about to generate intelligence. And this is now related to this goal that we've started working on maybe in the last 5 years or so, which is the goal of developing causal representation learning. So because just like classical AI or symbolic AI, standard causality has the problem that these structural causal models are usually at the symbolic level. So they assume that the causal variables are already given. And however, there's maybe we can call this a core problem of causality. There's the opposite problem, or an orthogonal problem in machine learning, which is what I've tried to bring across thus far in the talk, which is that standard machine learning or representation learning only learns statistical representations. So it represents correlations, as more generally statistical dependencies, but it doesn't capture interventions, reasoning, and planning. So these are two problems of those two different fields. And the hope of causal representation learning would be that it's somewhere in the middle and it addresses both problems at the same time. So the hope is to build representations that go beyond that, representations that support interventions, data set shifts, etc., but that are still automatically learned from data. And I think if this succeeds, it will also have major implications for medical image processing. And to this end, to structure the problem a little bit, I want to go back to the independent mechanisms assumption and to this factorization of a joint distribution according to the graph. So that's our factorization. And basically this factorization is possible because the noise terms in this structural causal model were assumed to be independent. So the noise terms being independent translates into this being a product over conditionals. But afterwards, I talked about this additional assumption, the dependent mechanisms assumption. And that's an assumption relating these different green things to each other for different values of I here. And sorry, this should be a lowercase I. And this assumption one could also state as saying that if we change one of those guys here, it doesn't change any of the other guys. So the other ones will remain invariant if we make a change on one of them. And now this, let's call this a disentangled factorization. And you might have heard there's a field of disentanglement in machine learning now. Usually that field just talks about statistical independence. It looks for latent representations which are statistically independent. Now that could be viewed as a special case of this thing, just for a disconnected graph. If there's no causal structure, no interesting causal structure, then maybe this is enough to talk about. But in general, I argue it's not. Now, if this is a disentangled factorization, what's an example of an entangled factorization? This is an example which is mathematically possible, no matter how you order the variables. So there are many such factorizations, but note that in this factorization, sometimes it might use quite a few terms back here, and this could be much more compact depending on how the graph looks. But more importantly, these things are just mathematical conditionals. There's probably no real world intervention that changes these, but these things here correspond to the structural equations. So these are, if you want, real world objects, and we can change these. And if we now change one of these, in this factorization, the other ones usually will not change, but in this factorization, probably everything will change at the same time. So this, it's not as nice. It doesn't behave nicely under interventions and under data set shifts. And data set shift from this point of view, if we think of this factorization, we would assume that typically if there's a data set shift, then as long as the two data sets are closely related, it may just be a sparse number of these mechanisms that changes, and the other ones will not automatically also change. So looking for sparse changes should thus be a good inductive principle to bias us towards causal factorization. And so we have some ideas now floating around how one could learn factorizations that are more causal. One is what I just mentioned. So this we could directly try to make sure, or I didn't quite mention. Actually, one is the one I just mentioned is to require that mechanism shifts are sparse, for instance, across domain shifts or across actions interventions. Another one would be to try to make sure that these different mechanisms are independent in some other sense. There's also the idea, and I'll show you examples about this, that interventions still produce valid data. So the representation should be such that if we change one of these variables, we still get something meaningful at the output. And finally, there's the idea to embed the DAG structure of structural causal models into neural networks. So let's see how far I get, but I want to show you a little bit of each of these. So this is this work on building in the structure of a DAG into a decoder. So we train an autoencoder, but the decoder kind of contains a DAG in a certain canonical representation. It's called the topological ordering. It just contains a structure that in principle can learn any possible DAG, and then the latent code is divided into chunks, each of them acting as the noise variable or as the U variable driving one mechanism. And this works surprisingly well, even though it's not explicitly regularized. So it leads to very good FID scores down here, and also small reconstruction losses in some of these tasks. We've also started applying it to medical data, but this is very much ongoing work, so I'm not going to talk about this now. A second example is about directly trying to learn components that are independent from each other. And here the idea is we have a system that gets data that looks like this. Each data point is degenerated by some mechanism. We don't label it by the mechanism, so we don't know what degenerated is. We just get a random mix of images like this. And from this, we want to learn we want to be able to undo these things, and we want to learn modules of the network that correspond to the different mechanisms. And that then ideally should also transfer to other kinds of data. And the architecture is like a kind of a mixture or competition of experts, which are submodules of neural networks that compete for data. So something comes in, the different experts try to explain it. Explain means to map it to something which sort of looks more like a canonical example, and the whole thing is trained like a GAN, a generative adversarial network. So there's a discriminator that says who is doing best, and then the gradient gets propagated back through the best one. And it works quite well. So we essentially get an accuracy which is very close to what we would have gotten without the noises. But more importantly, it also generalizes or transfers to other problems. So here to this omniglot characters, which it hasn't seen during training. So it can also undo these kinds of transformations. So yeah. We have since extended this to the recurrent setting, to a more complex architecture, which is called recurrent independent mechanisms. But I don't want to talk about that now. Instead, I want to now show you, I think, two examples that are closer to the idea of counterfactuals or interventionals. And first one here is a work of Michel Besselb in my lab. So here the idea is we want to train generative models for images, and we want to find modular internal representations in such generative models, and we do this by training them and then clustering or grouping together neurons across different layers and also inside layers that jointly control aspects of the image, and which thus should be or could be manipulated as a bunch. And then we manipulate them using a special technique which we call hybridization. So we basically take one module from one input example and combine it with another module that's taken from another input example. So in this way, we can produce a hybrid of two different input examples. and this is so it allows, for instance, intervening on just the background and changing the foreground. So this is an input image, and this is a completely counterfactual image, which is kind of saying how would that image have looked like if the background had been the one that's from a different training example. And I think it looks quite interesting. Here's some more examples where we take, for instance, here we have an image of a koala, here an image of a teddy bear, and this in between is a completely synthetic image which combines aspects of the two, and which I think looks a little bit like a koala teddy bear. Yeah, so this is another piece of work that's going in a somewhat related direction. So I think you probably all heard of self-supervised learning, which is very much a popular area these days, an interesting approach to unsupervised learning, to sort of generating supervised problems out of unsupervised ones. And in particular, self-supervised learning like SimClear has made a lot of progress using what's called image augmentations. So these are operations that you apply to an image which change some aspects while leaving the semantics or the image content invariant. So this should always be still considered a dog, but the images look quite different. So so we can interpret these augmentations, and that's the content of this paper, as a kind of an intervention on the image style as opposed to content. So we think of the dog as being the content, and all the rest, all this variability, we think of as the style of the image. And we can formalize it as a causal latent variable model, where we have style and content, and then we have the original and augmented images, and we get pairs of such images. And we can in this model we can actually prove that we can identify the invariant content from this kind of pairs of data points. So, okay, so there's another paper that I don't want to talk about so long, but it's I'm just giving a few examples from different areas. So this is closer. It's also trying to learn causal representations, but this one is building on something which is called invariant risk minimization. But it extends the idea of invariant risk minimization to the nonlinear case by using and connecting it to the theory of what's called identifiable VAEs, so variational autoencoders. And I think maybe I don't have time to talk about this more right now. Yeah, so maybe I want to also briefly mention this. This is a work in progress, hopefully on arXiv soon. So the idea in this invariant risk minimization, maybe so much I have to say, is that if we can find out which of the features surrounding the quantity that we want to predict are causal as opposed to just confounded or even anti-causal, then if those mechanisms, the causal mechanisms, remain invariant, then by identifying those causal features, we should be able to find classifiers that work across these changes. So that's the invariance idea. But in practice, it's not always the case that we predict, for instance, the image label only from its causes. In a certain sense, a label is actually more like the cause of the image. So we, in diagnostic applications, we are actually closer to an anti-causal setting than a causal one. So, so this idea of invariance doesn't always solve the problem for us. But there are some things you can also try to do in the anti-causal setting. And this work here in particular looks at the problem you could call measurement or sensor shift. And so here's and the idea here is that if these shifts between different distributions are happening on a relatively low level, so on the level of measurement, then you can sometimes compensate for them very well if you just adapt not so the first level that computes the representation, which would be closer to the previous paper, but you adapt at the very end, and you adapt such that the distribution of the layers just before the end are as similar as possible as they have been in the data on which you originally trained the system. So I think that's a promising direction also. And We have a number of, we're starting to connect this more and more to robotics, to real world data where we actually can do the interventions. So we have started collecting robotic benchmark data, and we have precise control over what are the causal variables, and we can intervene on the variables. So this is something that we started 1 or 2 years ago, and it's still very much ongoing. And we have a benchmark where people can even submit their code and run them on robots that run in our basement. And we use this overall framework to study robustness in transfer problems. And this includes also the transfer from simulation to real data and so-called out of distribution generalization. And here in this paper, we look at whether disentanglement in the statistical traditional sense actually is a good predictor for robustness, and that doesn't always seem to be the case. Yeah, this is another robotics project that I will skip over, and also this one, a very recent robotics project. Yeah, I want to say a little bit about this one, which, because I think ICA is also sometimes used in medical applications, and I think this is quite interesting development, and it directly connects to this independent mechanisms assumption. So nonlinear, I mean, I think most of you know linear ICA. You have some sources, you have linear mixing process, you have some observations, and then from the observations you want to reconstruct the sources under the assumption that the sources are statistically independent. Now, in the linear case, that's possible up to certain degrees of freedom. In the nonlinear case, this is a hard problem and impossible in general, unless you make some strong assumptions, and people have recently come up with interesting assumptions. We want to, and these are typically assumptions about statistical dependence or conditional statistical dependence of the sources. Now, we want to put in some additional knowledge. We want to put in independence, not statistical independence between sources, but in addition, we want to put in independence of the mixing processes. So we interpret this as a causal process, and we want to constrain the mixing function, which is now a nonlinear one, using this ICM, this independent causal mechanisms principle. Now, we cannot directly apply it because usually we assume, the way I talked about it before, we assume that this refers to an independence between the cause distribution and the mechanism, which is the conditional of effect given cause. But in our case, we don't have the cause. We want to reconstruct the causes, these sources. And so we use a different kind of assumption, which is we look at the different components of this mechanism, this mixing mechanism, and make an assumption about how these different parts of this mixing mechanism act relative to each other. And you can, I mean, often ICA is motivated by this cocktail party problem. So in the cocktail party problem, traditional ICA solves it by saying, I have two microphones, two mixtures of two speakers, and I want to reconstruct two original sources which are independent from each other. So we now require that a little bit more. We require something about the mixing mechanisms, namely that if you want that the speaker's positions are not fine-tuned to the room acoustics and to the microphone placement. And mathematically, the assumption will be that via a certain condition on the Jacobian matrix of the mixing function, it's a certain orthogonality assumption between the columns of Jacobian. And I think that's about as far as I want to go into this now. Yeah, it turns out that this has a number of nice properties. It avoids a number of the counterexamples that people have come up with, why nonlinear ICA is hard. But I think this is about as much as I should say here. So I like to think of images and scenes as causal generative models. And maybe as just a very last example, we've recently built such a generative model for a class of scenes that we get from aquarium videos. And this causal generative model is structured such that we can make interventions. It doesn't generate the whole thing in one go like a GAN, but it generates it in a structured way, such that we can intervene on fish identities, positions, number of objects, background, etc. So I think I have to wrap up now. So the overall goal is we want to learn world models, or maybe in more modern lingo, digital twins that are data efficient, so that pool data from multiple tasks in multiple environments. They need to, in order to be data efficient, they need to reuse components, and to be able to reuse them, they have to be robust across tasks. And I think a good candidate are quantum mechanisms. And these world models should be interventional. And overall, we want to move representational learning towards representations that support Konrad Lorenz's notion of thinking. He once said thinking is nothing but acting in an imagined space. So they support planning and reasoning. And if you're interested in this, we recently published this position or this overview paper on this topic. And I would like to thank my whole lab for the research that I talked about today. Thank you very much.
Bernhard, for this fascinating talk. We have one question from the chat. So Kiran Vadya Venkadesh asks, what do you think of the MLP mixer? Recent research from Google shows that an MLP-based architecture is as powerful as transformers for image classification. It feels like we're going back in circles.
Yes, so I think in general in this field, there's this problem of credit attribution, not in the sense of who gets credit for which research, but in the sense of someone introduces a little novelty and then runs a lot of experiments, it gets better results, and then we attribute everything to that. And then a year later, someone else get back and takes an old architecture and puts a lot of effort in and new GPUs and gets better results with that. So it's hard when new results come out, it's hard to really attribute what is due to architectural novelties and what is due to more compute power, etc. And I think it's also partly the fault of the field, that whenever someone has a new idea, we require that the results have to be better. It biases the whole field towards just making sure and squeezing the last bits. I mean, the PhD students try harder and harder to get the best results. And in the end, it makes it a little bit hard to really understand what is actual progress and what isn't.
That's a great answer. I would like to ask a question myself. One of the problems I'm working on is motion management in robotics, and we quite often observe motion deformation in a human. For example, someone breathes and that deforms the liver. Do you believe, for example, that this deformation of an organ that we see, for example, in MRI or in ultrasound data, could be something that can be solved with a causal learning process, so that we can say the causality is the motion and the actual thing we're observing is always the same? At the moment, we're trying to match those deformed images, of course, and that doesn't really work all that well.
Yeah, that would be fascinating if we could somehow come up with a causal sort of latent variable model that where we have this latent process about the deformations, and maybe I guess the question would be what kind of data to train it on, whether we could, maybe we could even have some interventional data where we explicitly make interventions and move the patient a little bit and see what changes. So I think that would be very interesting. Yeah.
Yeah. Do we have time for one more question? Do you have one more question, Jan?
Well, my question would basically be, I mean, do you think it's always going to be necessary that we as humans are going to have to input some assumptions about the causalities? Or I think, I mean, as a human, I have a very strong, well, at least opinion on what is the cause and effect. And in a way, that's also just gathered from maybe statistics and maybe intervention. So do you think that's going to be all possible to all automate, or are we going to need the human still for some modeling aspects?
Yeah, I mean, I think humans are very good at transfer. So we are quick at making causal judgments, but the reason why we can do it is that we have this huge domain of experience and common sense that we transfer from other problems. And right now, most of our AI systems are these idiots that focus on one task. And as long as they are like that, this additional knowledge of common sense has to be somehow baked in or built into these systems by us. But as we move towards more general agents that also transfer to some extent, I would hope that the amount of additional side knowledge that we have to put in will correspondingly go down over time.
Great. Well, thank you very much for the really, really interesting keynote. It's been a pleasure having you here, Bernhard. Thank you so much for your time. And if you have the time, feel free to explore our virtual conference venue. And otherwise, I wish you all the best, and I'll hand back to Alex.
Thank you.
Even the greatest keynote lectures have to end eventually, and now there's no time for many words, but I would like to hand over to our chairs, Maria and Ari, for the image acquisition and reconstruction long oral session. Thank you. See you there.